The paper titled Development of Resistive Plate Counters by R. SANTONICO and R. CARDARELLI discusses the creation and testing of a particle detector known as the Resistive Plate Counter, RPC. This detector is designed with two parallel electrode plates made from bakelite, a material with high bulk resistivity, separated by a small gap filled with a gas mixture of argon and butane at ordinary pressure. The RPC operates at a voltage of about 10 kV, achieving a high efficiency of 97% and a time resolution of approximately 1 nanosecond without the need for signal amplification. The output pulse typically measures 300 millivolts over 25 ohms. The RPC works by generating a constant and uniform electric field between the two electrode plates. When a charged particle passes through the gas, it ionizes the gas, causing a discharge that is confined to the region near the particle's path due to the high resistivity of the electrodes. This prevents the electric field from spreading and ensures that the counter only responds to the region where the particle passes. As a result, the RPC can accurately detect the presence of particles without interference from other regions. One of the key advantages of the RPC is its simplicity. The design eliminates the need for high-pressure gas systems and mechanical precision, making it an economical alternative to other particle detectors like plastic scintillators. The low requirements for mechanical precision also make it easy to build the detectors in large dimensions. The prototype RPC described in the paper has a sensitive area of 85 by 13 centimeters and consists of two parallel plates connected to the high voltage supply. The ground electrode is made from a bakelite plate coated with a conducting foil, while the high voltage electrode is a similar bakelite plate coated with a thin foil of conducting paper. The high resistivity of the bakelite and the coating materials ensures that the RPC is transparent to electric pulses generated within the detector, which can be read through copper strips outside the counter. The authors conclude that the RPC offers better time resolution than wire chambers or limited streamer tubes due to its uniform electric field, which reduces the time fluctuations caused by electron drift motion. Additionally, the RPC's ability to operate at ordinary pressure with a simple gas mixture and low mechanical requirements makes it a practical choice for a wide range of applications in particle detection. The paper outlines the potential of RPCs to replace plastic scintillators in situations where large detecting areas are required but high fluxes of particles are not necessary. The development of this technology represents a significant advancement in the field of particle detection, offering a new tool that combines simplicity, efficiency, and cost-effectiveness. The next section of the paper describes the physical construction and experimental setup of the Resistive Plate Counter RPC prototype. The prototype consists of two identical counters, rigidly superposed on one another, sharing the same copper foil as a common ground plate. The structure of the RPC is illustrated in Figure 1 of the paper, showing the different components, including the bakelite electrode plates, insulating PVC plate, and the gas input system. The bakelite plates, coated with a thin foil of conducting paper, have a surface resistivity of about 1 megamamps per square. This high surface resistivity allows the foil to be transparent to electric pulses, meaning the pulses generated within the counter can be detected by copper strips placed on the outside of the PVC plate. These strips are arranged in such a way that they are separated by about 2 millimeters, creating a characteristic impedance of 50 ohms. The two electrode plates are separated by a 1.5 millimeter PVC frame, which is used to maintain the structure and also contains the gas within the chamber. The entire assembly is glued onto the ground electrode, forming a rigid panel that can be easily opened if needed. The conducting paper, which is isolated from the high voltage, is connected to the copper foil for grounding purposes. For testing, a systematic experimental setup was developed using cosmic radiation as a source of particles. The setup included 3 identical scintillation counters, designated T1, T2, and T3, along with a lead screen to absorb electromagnetic showers. The tests measured the efficiency and time resolution of the RPC by examining the pulses generated when charged particles passed through the counter, with output pulses ranging between 200 and 400 millivolts. The authors found that the pulses exhibited a rise time of just a few nanoseconds and were successfully detected using standard coaxial cables connected to a discriminator. The results confirmed that the RPC had good efficiency and timing characteristics, making it suitable for applications requiring precise particle detection. This section highlights the practical aspects of the RPC design, emphasizing its simplicity, mechanical stability, and the ability to produce reliable results in detecting particles with a high level of accuracy. The experimental setup and testing confirm the effectiveness of the RPC as a particle detector, laying the groundwork for its potential applications in various scientific and industrial fields. In this section, the authors describe the performance of the resistive plate counter, RPC, through a series of tests that evaluate its efficiency and time resolution. First, the efficiency of the RPC was measured by using a setup where cosmic rays were detected by 3 scintillators, T1, T2, and T3. These scintillators defined a beam with a cross-sectional area of 3 by 60 square centimeters, which was used to evaluate the RPC's response. The efficiency, denoted as epsilon, was calculated by comparing the rate at which the RPC detected particles, denoted as C, to the rate at which the scintillators detected particles, denoted as T. The formula used is epsilon equals C divided by T. The results, shown in Figure 3, indicate that the RPC reached a maximum efficiency of 97% when the applied voltage was around 9 kilovolts, kV. The authors also investigated the pulse amplitude generated by the RPC. This was done by varying the discrimination threshold, which is the minimum signal level that the detector would consider as a valid event. The efficiency of the RPC was measured for different thresholds. Figure 4 shows that when the particle crossed the strip directly, the pulse amplitude was, on average, around 300 millivolts MV. However, for particles that crossed a neighboring strip, the pulse amplitude was significantly lower, averaging about 50 millivolts MVs. The time resolution of the RPC was assessed by measuring the delay between signals from the RPC and a small scintillation counter, T4. The distribution of this delay is shown in Figure 5. The full width at half maximum, FWHM, of this distribution, which gives a measure of the time resolution, was found to be 1.2 nanoseconds, ns. The graph also shows a short tail, which the authors attribute to delayed pulses from the RPC. In summary, the results highlight the high efficiency of the RPC at around 9 kilovolts, a clear distinction in pulse amplitude based on the particle's path, and a time resolution of approximately 1.2 nanoseconds. These findings underscore the suitability of RPCs for applications requiring precise timing and efficient particle detection. In this final section, the authors discuss additional findings and conclude their study on the resistive plate counter, RPC. One of the key observations is that the discharge within the counter is highly localized, with the region of discharge being much smaller than the width of the detection strip. For a single strip with a sensitive area of 255 square centimeters, the rate of pulses observed was 35 Hz at a voltage of 9.5 kilovolts, with a discrimination threshold set at 240 millivolts. The time resolution of the counter was further analyzed using a small plastic scintillator NE110 with dimensions of 10 by 6 by 2 centimeters. The scintillator's output pulses were shaped by a Lecroy Model 621 CL discriminator, and the timing was measured using a time-to-amplitude converter. The timing data revealed that the distribution of delay times had a full width at half maximum, FWHM, of 1.2 nanoseconds, confirming the high time resolution of the RPC. In conclusion, the authors highlight that the detection technique presented in this paper offers a significant advantage in terms of simplicity and cost-effectiveness. The use of plastic scintillators in large area detectors, such as those required for neutrino physics or proton lifetime experiments, could benefit greatly from this technology. Additionally, the excellent time resolution makes this technique highly suitable for applications requiring precise time-of-flight measurements. The paper ends with acknowledgments to those who contributed to the research and a list of references for further reading. This concludes the study on the development and performance of resistive plate counters.